All attendees are in listen-only mode.
Well, hello, everybody, and welcome. This is Hot Rod coming at you from Missouri. Just got back from a road trip, and we've got a very exciting webinar today. We've got our largest ever attendance. I think you're going to enjoy this one. We've got a good friend of mine and an industry legend, John Siegenthaler, is going to lead us through a really, I think you'll find it an informative and interesting thing. And I know John's been in the industry a long time, and he's taught me a lot, and I'm sure a lot of people out there have learned a lot from what he's given us over the years. So I'm going to kick it off. We're going to go through it. We've got a lot of slides to go through. Hopefully we can have some room at the end for questions. If not, there's going to be a part 2 and part 3 to this GEO, we'll call it session here. So if we don't get to all the questions today, maybe when we open the next one, we'll answer it. And certainly I'll answer them all via email, but I'd like to get to some on the air so we can all benefit. So with that in mind, thanks again, John, for joining us and putting this together, and it's all yours.
Thanks a lot, Rod. And good afternoon, folks. Hopefully you're all looking at this slide, GEO-hydronics Part 1. And you might be wondering, what's this term GEO-hydronics? This session and the two that are going to follow it are really about leveraging hydronics to enhance the performance of heat pumps, be it ground source heat pumps or other types of heat pumps. We're going to go through several different topics today. I've got a listing here on this slide. Many of these are basic topics. I'm assuming quite a few people in the audience are relatively new to geothermal heat pumps or heat pumps in general. So we're going to talk briefly about the different configurations of heat pumps. We'll take a look at some graphics that explain where the heat is coming from, where it's going to. We'll talk a little bit about the performance characteristics of heat pumps. Applying a heat pump in a hydronic system is different than applying a boiler. The heat pump its performance is very much determined by water temperature that the distribution system operates at, as well as the water temperature of the earth loop. And designers need to be very cognizant of those performance characteristics. We're also going to look at some earth loop configurations. The geothermal heat pump topic is like the solar topic. It's a very, very broad topic. So we aren't going to get into great depth on sizing earth loops. I do have some rules of thumb, but we also have a reference that I'll give you that has more complete information on sizing up those earth loops. Another thing we're going to take a look at are manifold-based earth loops versus what I'll call the North American traditional approach, how this piping is put together out in the trenches versus the option of collecting those earth loop circuits into a manifold that could be either inside the building or outside the building. And as Hot Rod mentioned, we've got Part 2 and Part 3 that'll get into more details on specific piping schematics with heating-only applications as well as combined heating and cooling applications. So let's talk about what's a heat pump to begin with. Well, a heat pump is essentially a refrigeration system. It's going to gather heat from some low-temperature material, which we call a source. When we talk about ground source heat pumps, the word source simply means the origin of the low-temperature heat. And then using this refrigeration process, it's going to upgrade the temperature of that heat and release it to what is technically called a sink. Nothing to do with that basin you wash your hands in. Simply, a sink is the material the heat is being dissipated into. So when we're talking about heat pumps that are used to heat buildings, there's several different sources. We can use outside air. There's, I'm sure, tens of thousands of what are called air source heat pumps that are in current service in North America as well as around the world. They gather heat from the outside air simply by producing a refrigerant temperature that's lower than the outside air temperature, and heat transfers from higher temperature to lower temperature. Groundwater. We will look at a couple of slides that show direct use of groundwater, be it from a well or a lake or a large pond, and then a closed-loop system where that heat is being extracted from the soil into a fluid, but that fluid is completely contained within a sealed earth loop. The fluid itself never comes in direct contact with the soil. And all these sources are providing free low-temperature heat. Ultimately, it's solar energy that's been stored either in the soil or in the water. Over on the right side of the schematic, you can see that cursor moving around, there's just some graphics that show the different combinations of sources and sinks, air to air, water to air. One on the bottom is one we're going to focus on quite a bit, water to water heat pumps, especially since we're, again, leveraging hydronics to enhance the performance of the heat pump. We want to take advantage of the very latest in hydronics technology to design our distribution system. For those that are very new to heat pumps, here's a basic diagram of a refrigeration system. Starting over on that left-hand side, you see there's a source media. We can just say that's water from the ground. We have that blue coil, which is representing tubing with a refrigerant in it. The refrigerant is absorbing heat from that source media, which is causing the refrigerant to evaporate. That vapor travels up into the compressor, and the compressor is operated by an electric motor. It's going to increase the pressure and the temperature of that refrigerant vapor, potentially as high as 160, 170 degrees Fahrenheit. That hot vapor then leaves the compressor, goes down through this red coil on the right side called the condenser. This is where heat from the refrigerant is transferring to our load medium, which in the case of a hydronic system would be the water going out through our distribution system. The refrigerant is hotter than that water at that point, so heat is flowing from the refrigerant to the water. And then finally, to get us back to the starting point, the refrigerant passes down through a thermal expansion valve, which drops its pressure and its temperature. And essentially, we're back to the starting point of that cycle. This is a very typical cycle. It's not only characteristic of a heat pump, but it would be a refrigerator, an air conditioner, a deli case. All systems use that. Basic energy flows within a heat pump. We have over on the left our free source heat, whether it's coming from the air or from the ground. That is that arrow going into the evaporator. We need electrical input up here at the top to keep the compressor running. So those two arrows are both pointing into the heat pump. Those are energy inputs. The first law of thermodynamics tells us that the energy in to a device has got to equal the energy out. So over on the right side, we have the higher temperature heat that's being dissipated to the load. And this little kind of picture equation down at the bottom of your screen just shows that the source heat input added to the electrical heat input, or the heat that's generated as the equivalent of the electrical input, those two add together to give you that output. Now, one of the nice things about heat pumps is that most of them are reversible, which means that effectively the evaporator and the condenser in the heating mode, which is what you're looking at over on the right side of the screen, those functions, the evaporator and the condenser, can essentially be flipped by the use of a reversing valve. It simply redirects the hot vapor coming off of the compressor either to the left or to the right. So the same machine that is producing warm water to heat a building in winter could also be used to produce chilled water to cool that building in the summer. And this is a fast process. This can happen multiple times in an hour, for example, if necessary. But it is certainly unique in the sense that boilers can't produce chilled water. Most of the heat pumps we're going to take a look at are considered to be reversible heat pumps. Now, here's kind of an interior illustration of an air-to-water heat pump. An air-to-water system would have an outdoor unit. You see it in the upper right-hand corner. This is basically drawing outside air through it and extracting heat from that outside air. And then the refrigeration cycle we talked about is shown down below. And the net effect of all this is to deliver heat to a stream of water, or it could be a mixture of water and antifreeze, that is going back into the building and going to some type of distribution system. So again, we're extracting heat from outside air, raising the temperature of that heat, and delivering that heat to a fluid stream that ultimately goes through the building's distribution system. Okay, now we're going to flip it. Instead of an air to water, we're going to do water to air. This would be a very typical heat pump in a ground source application where either groundwater, as you see here in the upper left, or water that's circulating through a closed earth loop is the source of the heat. Again, the refrigeration system upgrades the temperature of that heat, and that heat is being delivered to a coil heat exchanger inside the heat pump, and the blower is drawing air across that coil. And in the heating mode, that is warm air. In the cooling mode, that air is both cooled and also dehumidified. And you'll see some droplets of water over here on the coil, just like any AC unit would have. So we're getting both latent and sensible cooling. Same concept, only with a water-to-water. And if you've been following these last couple of slides, you'll see that it really is the same concept. What's changing is, in effect, the heat exchangers within the heat pump. Is it a heat exchanger for refrigerant to water, or is it a heat exchanger for refrigerant to air? And by various combinations of these different heat exchangers, we can build these different heat pump configurations. So again, a reversible water-to-water heat pump, of all these heat pumps we're going to look at, is probably the most versatile because it can take full advantage of a wide range of hydronics technologies. Again, just a slide we borrowed here from Climate Master, one of the manufacturers of heat pumps. It essentially shows a water-to-air heat pump both in the heating mode up here as well as the cooling mode, and really just summarizes what we talked about. Now, here's a long list of benefits of geothermal heat pumps. I'm not going to read all these off to you. There is a PDF file that will be made available of all these slides, so don't worry about copying all these down. If you'd like to get that PDF, we'll tell you how to do that. But you'll see there's a lot of advantages here with geothermal heat pumps. Things like high performance characteristics, high coefficients of performance, which we'll talk about shortly, longer service life, reduced noise because you don't have an outside unit. It may be an advantage if there's no need to bring gas service to a house. Certainly you're going to save the basic service charge associated with that gas meter. So there's a lot of advantages of using that technology. Now, these are just some photos that illustrate it. I like to collect photos like this. Some of these are, that one on the left you see is fairly recent, October 2009. That was published in a building magazine. It shows some brand new townhouses. And I'm sure that the photo was meant to highlight the aesthetics of those townhouses, but take a look at that red arrow. Right below the deck on all those townhouses are condenser units. And of course, many of you know what those sound like in the summer. You've got a fan running and you've got a compressor in there. And if the idea is to go out on the deck and spend a nice relaxing evening out there, you're going to contend with the noise and possibly even some airflow from that. Over on the right, same idea, just basically noise right next to the deck. And of course, this scenario gets repeated many, many times over because of somewhat arbitrary location of these outdoor condenser units. Obviously, heat pumps don't involve combustion. And as such, we eliminate any issues with venting combustion products, whether it is how to get those vent tubes out of the building without producing these plumes. This is one in the upper right is one of my favorites. I'm not sure who did that, but that's not really a good idea. You're going to have a lot of ice on those steps if that's a cold climate. And down in the lower right here, again, somebody that wasn't reading the installation manual as far as clearances to windows. So this all disappears with heat pumps, as does on-site fuel storage. No need to have fuel oil tanks, propane tanks in the lower left. That's what happens when you don't anchor an underground propane tank and it's empty and the soil gets saturated. It turns into a submarine. So again, just some details or some issues that go away with heat pumps. I mentioned the basic service charge for gas. The idea of an all-electric house with a heat pump that can both heat and cool. If gas is not being used for any other purpose, in this case, in my local utility, that'd be eliminating almost $18 a month, just the basic service charge plus the first 3 therms of gas. Now, geothermal heat pumps are eligible for a 30% uncapped federal tax credit. There may be other incentives available depending upon the state, some state tax credits or some other grants. You'll see some wording over here on the right. I can't tell you specifically exactly what portions of the system are qualified. My suspicion is that certainly the earth loop, the heat pump, any equipment associated with connecting that earth loop to the heat pump, I'm sure that would be covered. But, for example, if it was a new house with a new radiant floor heating system installed as the distribution portion of the overall system, my speculation is that probably is not covered by the tax credit. Even though it is part of the system, it would also be part of a system if a boiler was being used or some other type of a hydronic heat source was being used. So I'll take the standard default and say consult your tax advisor on that. But still, that 30% uncapped federal tax credit is going to be an attractive incentive to go with geothermal heat pumps. And by the way, I'll just go back to that. The website, many of you are probably familiar with this website, dsireusa.org. That's the database of state incentives for renewable energy. It's a database that is run by the DOE, and it's frequently updated with what the latest incentives are, federal level, state level, and I certainly would recommend that you take a look at that. Now, again, water-to-air geothermal heat pumps. We've looked at the refrigeration system. I just want to point out up at the top, you can get these heat pumps in a couple different configurations. Horizontal configurations are nice if they're going to be mounted under a floor or above a ceiling where you have restricted, limited vertical space. The vertical units are probably more typical in residential where it's mounted in a basement. Really, performance-wise, they're more or less identical. It's just the physical geometry of the hardware that allows two different configurations. And most of the manufacturers offer a range of models in both horizontal and vertical cabinets. Here's a slide that shows what I call a typical North American installation. See the heat pump on the left side here, a vertical cabinet with a flow center or flow controller. And there's a graphic over here on the right. It's essentially a combination of, well, anywhere from 1 to as many as 4 circulators and a couple 3-way ball valves that are used for purging. Various manufacturers put these together to create a module such that you simply run a couple flexible hoses from this flow center over to the heat pump and then connect the other side of the flow center to the earth loop. It's nice. The one thing that I personally don't get too thrilled about is 4 circulators at 250 watts apiece. That's 1,000 watts going into circulating an earth loop. My reaction to that is design a better earth loop with less power requirements, and that's definitely possible. But we're going to use this as kind of a starting point just so you have a reference. You do see over on the right side of that schematic a water heater. Many heat pumps have an extra heat exchanger between their condenser and their compressor, and that's called a desuperheater. The desuperheater takes the hottest gas off the compressor and uses it in combination with a small circulator to preheat domestic water. And this is especially valuable in the cooling mode. In the cooling mode, the heat that is being rejected by the heat pump, if you don't have a domestic water setup with a desuperheater, all that heat goes into the ground. If you do have a domestic water setup with a desuperheater, some of that heat is literally free to heat your domestic water, preheat your domestic water. So in climates that have strong cooling loads, a desuperheater makes a lot of sense. And these are available both on water-to-air as well as water-to-water heat pumps. This slide shows you some pictures of various water-to-water heat pumps. You'll see the cabinets. Here's one from the European market, looking at that thing at a trade show. Honestly, if you put arms on that, you could call it a robot, I think, R2-D2. But that is, in effect, a water-to-water heat pump from a company called Rotex over in Germany. So these technologies are used worldwide, and the Europeans in particular over the last few years have have become a very strong market for water-to-water as well as air-to-water heat pumps. Now, I mentioned that this term geohydronics is about leveraging hydronics to enhance the performance of heat pumps. This is a slide that essentially compares what we're doing with hydronics up at the top with a small circulator, perhaps with an ECM motor, and some small diameter flexible tubing, what we call a home run distribution system. These are pretty much state-of-the-art hydronics versus a blower and some interestingly hung flex duct there. Kind of ask the question, how long can you get those nylon zip ties? The advantages of hydronics are independent of the heat source. Water is a tremendously more effective material to move heat around a building compared to air, and that certainly holds true with heat pumps. Now, just to show you that, I did a little comparison. I like to use an index called distribution efficiency. And what it is simply how much heat is, or what's the rate of heat delivery divided by the wattage of the delivery system, the input wattage required to operate the delivery system, not the heat source, but the pumps or the blowers. So I took a case of a nominal 4-ton rated water-to-air heat pump and actually looked up some manufacturer's information, and that heat pump, the standard heat pump with the PSC blower, permanent split capacitor motor in the blower, requires a little over 1,000 watts to operate that blower. So if we're delivering 48,000 BTUs per hour on about 1,000 watts, we get this index for delivery efficiency or distribution efficiency. About 44 BTUs per hour are being delivered per watt of input to the distribution system. Now, again, this is the forced air distribution system. So let's compare that to a hydronic system. And actually, this is a pretty conservative comparison. We could easily deliver 48,000 BTUs per hour in a hydronic system with an 80-watt circulator. In fact, today with good design, you could probably do that on about 20 or 25 watts. So even at 80 watts, you'll see that the distribution efficiency is much higher. And the implication here is that in this particular comparison, our hydronic system is delivering heat to the building using only about 8% of the electrical wattage of the forced air system. So while the thermal efficiency of a geothermal water-to-air heat pump is good, the fact that it still uses forced air to deliver that heat is still somewhat of a Achilles heel in terms of overall energy use. So why not combine that high thermal efficiency of the geothermal heat pump, excuse me, with the very high distribution efficiency that modern hydronics offers? Again, I'm going to go through this. I'm kind of skipping over this one quickly. It's just the internal refrigeration system in a water-to-water heat pump. We've talked about the inputs, the outputs. I do want to stop on this slide. Several things that designers need to realize about heat pumps. One is that their heating capacity, if you look at the graph on the left, their heating capacity, the number of BTUs per hour they produce, is very dependent on the source water temperature. This could be the temperature coming in from the earth loop or coming in from a lake or a pond. And you can see as that source water temperature goes up, the capacity of the heat pump goes up, and by quite a bit. The other thing the graph tells you is that the heating capacity depends on the water temperature of the distribution system. Anything that we can do as designers to reduce the water temperature in the distribution system will enhance the performance and the heating capacity of the heat pump. It's a simple rule, but it's a universal concept with heat pumps. Anything that you can do to bring that distribution system temperature down. That may mean closer tube spacing in a radiant floor, or larger panel radius, or perhaps a combination of the two. So we want to keep that distribution system as low in temperature as possible. Over on the right, that graph shows the effect of flow rate through the heat pump. As you increase the flow rate through the evaporator side of a heat pump, you are going to get better performance, and that's because that convection heat transfer improves with increased flow rate. However, the downside of increasing the flow rate is higher head loss, and that higher head loss leads you back to things like higher wattage circulators for the earth loop. So there's a trade-off there, and a typical rule of thumb is 2 to 3 gallons per minute per ton of heat pump capacity, and a ton is 12,000 BTUs per hour. So a typical 3-ton residential system would operate at about 9 gallons per minute maximum, and could actually operate down at about 6 gallons per minute. Manufacturers can provide a minimum flow rate requirement. Let's talk about efficiency, coefficient of performance. This is the index that is used to describe all heat pumps. And it's a very simple idea. If we go back to our energy flow diagram in the heat pump, we have a heat output, which is our desired result of running this heat pump. And we have an electrical input, which is the necessary input that we're paying for. We aren't paying for the free heat over here. Obviously, we pay to install the earth loop or whatever we are using to gather that heat. But the heat itself is free. So if we look at the desired output divided by the necessary input, and this is just kind of a picture equation again, desired heat output divided by electrical input, that is a coefficient of performance. And the goal in any system with a heat pump is to maximize that coefficient of performance. Now the graph shows you that the coefficient of performance on a heat pump, just like heating capacity, depends on the source water temperature. As the source gets colder, the COP goes down. So we're losing not only capacity in the heat pump, the BTUs per hour output, but we're also losing on the efficiency. Likewise, anything that you can do to lower the water temperature that the distribution system operates at is going to improve the coefficient of performance. This ELWT you see over here, that's entering load water temperature. This would be the water temperature coming back from the distribution system and going into the condenser of the heat pump. So again, a very low temperature distribution system is going to enhance that COP. And whatever we do as designers, we want that COP to be as high as possible. I like to think of it this way. I look at it as sort of a temperature lift. You can think of your source water at some temperature, be it from the ground or an earth loop, and that heat is ultimately going up into your low water. So I look at the difference in temperature from the source water up to the load water as the temperature lift. Anything you can do to decrease that lift is going to improve coefficient performance, and it's also going to improve capacity. So simple way to think about it. Very briefly, we'll talk about cooling. Heat pumps that have reversing valves can produce chilled water. This shows you total cooling capacity, and it's a function of, if we look down at the bottom here, the entering source water temperature. Now, we have to be careful with our wording here. The source now, in the cooling mode, is actually the interior distribution system in the building. That's the source of the heat in cooling mode. So this is the water temperature returning from the distribution system. The ELWT in the upper right corner, that is the entering load water temperature. It says temperature of water entering heat pump from earth loop. And you can see that the cooler the earth loop remains during the cooling season, and the warmer the distribution system, and this is now the chilled water distribution system, the warmer it can operate, the better the performance of the heat pump. So again, think of that temperature lift. Anything that brings the temperature difference between the source and the sink of the heat together is going to improve performance. In the cooling mode, rather than use COP, the industry uses another index called EER, Energy Efficiency Ratio. It's similar to COP, but the units are a little different. It's actually the cooling capacity in BTUs per hour over here divided by the electrical input in watts. So instead of converting the top and bottom of this fraction to the same units, it's left as BTU per hour per watt. Again, the idea is to maximize the energy efficiency ratio. How do you do that? You keep down at the bottom, you keep the earth loop as cool as possible in cooling season, and you keep the load water temperature. Now this is water temperature going off to your chilled water distribution system. Keep that as high as possible, but still providing moisture removal. If that water temperature gets too high, you won't be able to condense water vapor. And obviously there you don't have good humidity control. So it is necessary to maintain a certain water temperature for proper latent cooling. Okay, now let's kind of focus in on heat from the earth. I mentioned earlier that heat is essentially all solar energy. The ground is just a storage media, kind of a seasonal storage media. So we have the sun shining here on the ground all summer long, and that heat is driven or dissipated down into the soil. The graph over on the right is an indicator of what the temperature of the soil is, and this is actually for prepared for Syracuse or upstate New York at different stages of the year. You can see the horizontal axis is the day of the year versus the depth below the surface. And that curve that's labeled surface, that has the widest temperature fluctuation between winter and summer. As we go deeper in the ground, you can see the amplitude of that curve decreases. You also see a phase shift to the right. That means that, for example, the maximum temperature at, let's say, 5 feet down doesn't occur when the maximum surface temperature occurs, which would be, looks like if we go down here roughly first couple weeks in August, but rather at 5 feet down it looks like it's occurring sometime in early September. That's beneficial to us, especially going into the fall in the heating mode, because as the outdoor temperature is decreasing and our heating load is starting to increase, we're actually still at close to peak temperature in a horizontal earth loop. This is a graph that you can find in an ASHRAE handbook. It basically plots the temperature of the water table below 25 feet. And I'm sure we have people from all over the country, but in upstate New York where I'm living, it's about 47 degrees. And actually, if you follow that isothermal through, you see in Milwaukee it's just about the same temperature. Now, the water temperature doesn't change much in these deeper wells because that solar influence is extremely light. The sun just doesn't really affect things below about 25 feet. Now, we're going to look at open-loop geothermal heat pump applications first. Here's one. I was actually involved in a project a couple years ago that used this system or something similar to it. Basically, there was a privately owned lake, about a 6-acre lake. And, of course, this is in upstate New York. That lake has got a lot of heat in it. It's also got a lot of cooling effect in it. So what was done is to put a submersible pump in a sleeve out in that lake, and it's supported up on a pedestal so it's not in the silt. And basically, when this heat pump system operates, this water comes back in through, goes through a filter, and then it goes through a stainless steel plate heat exchanger. And that effectively separates that lake water from the water that's in the closed loop remaining portion of the system. We did that because we honestly don't know exactly what's coming up from that submersible pump. We could have, for example, a big rainstorm and a lot of runoff into that lake, and we might get some turbidity. We don't want to pump that through those heat pumps and foul out those heat exchangers. So we've got an automatic blowdown filter and a heat exchanger. Beyond that, over to the left, we've got multiple heat pumps. In this case, each one of them has a zone valve or a motorized ball valve that would open when that heat pump is operating. And we're combining that with a variable speed pressure regulated circulator. And that combination, some of you I'm sure will recognize, that's really the same thing we do with many systems with zoning, hydronic systems for zoning. We use valves that open and close and a variable speed pressure regulated circulator. And this is what I mean about leveraging the state-of-the-art hydronics in combination with the thermal efficiency of the heat pump. So that's one way you could do it. Here's what has come to be known as a pump and dump system. This is where we have a drilled well with a submersible pump. In all likelihood, this well could also be supplying domestic water to the building. And we've got a standard compression tank and a pressure switch that operates that submersible pump. So again, just like a standard domestic water well supply system in the building. And one of the loads we're putting on this now is the heat pump. When the heat pump turns on, the controls will open a solenoid valve, which is going to allow this pressurized water in the compression tank the flow through the evaporator. We have a flow switch there. The flow switch verifies that there is water flow before it will allow the compressor to operate. If the pump was not operating, or for whatever reason there wasn't sufficient flow, we don't want to turn the heat pump on. If we did that, we'd probably just end up having the heat pump trip itself off on a safety. And then we have a flow meter down here that tells us how fast that flow is going through, and a throttling valve. This is an application where we want to minimize the water flow through the heat pump simply because it reduces the amount of energy that our submersible pump requires. If we can operate that heat pump safely at perhaps 2 gallons per minute per ton, we're going to adjust this throttling valve and watch our flow meter and keep that flow as low as we can and still get acceptable performance. Now, there's 2 things that I like to say with these open loop systems. The 2 keywords, water quality and water quantity. You have to make sure you have sufficient water quantity. Obviously, if you have a well that's not a high producer, keep in mind that this a 3-ton heat pump could draw as much as, say, 9 gallons per minute, and that's what, 540 gallons an hour. Multiply that by 10 or 12 hours a day, you're pumping several thousand gallons a day of water out of this well. The well has got to be certified that it can sustain that. The second keyword is quality, water quality. The only way that I would consider safe doing one of these systems is to have a water quality test done by a professional water testing lab, know exactly what's in that water, and then verify with the heat pump manufacturer that those levels of whatever is in that water are within acceptable levels from that manufacturer such that that water can go directly through the heat pump. Silt, sulfur, or hydrogen sulfide, various bacteria, this can all end up plugging up the heat pump. And specifically in the cooling mode, when the hot refrigerant is going through that water-cooled condenser, that's where you tend to plate these things out. So make sure you have the water tested for quantity and quality before you commit to that. Now, getting away from that, we go to closed loop. This is, again, where we have buried piping. And here's an example of what's called a slinky earth loop field. Each one of those slinkies circuits is rated for about 1 ton worth of heat pump. So that's about a 6-ton slinky field you're looking at. We have the buried earth loop. We come into the building, and basically we have a circulator that pumps it through the heat pump. Now we're going to look at some more details of that earth loop. Here's a horizontal earth loop, actually 3 different configurations for horizontal earth loops, depending on the excavation equipment and the characteristics of the soil. A chain trencher, ditch witch, as they're commonly called, could be used to build this type of a earth loop where you have a very narrow trench in the ground with a couple pipes in it, 6 feet deep. If it's a backhoe or an excavator with a 2-foot bucket, you could do the one in the middle, put 2 pipes down 6 feet. And then the one I tended to like, we've used this on several projects, we call it a 4-pipe square. It's a 2-foot wide trench, nominally 6 feet deep. 2 pipes are down at the bottom. These 2 pipes, of course, would be laid in when the trench is dug. And then out at the end of that trench, the pipes are going to do a U-turn. We're going to put about 2 feet of fill back in the trench, and these pipes are going to come back at the 4-foot level. And then the remainder of the fill goes in. You see that yellow material around the pipe? That is only if there is very sharp rocks in the excavation. If it's a reasonable soil without a lot of sharp or very large rocks, the same soil can go right back around the pipe. It doesn't have to have any specific fill around the pipe. Again, slinkies we looked at. There's a nice shot of slinkies being covered up. That looks very organized, very neat. There's a lot of dirt that's been moved in that hole there. That's probably the equivalent of digging a couple basements. So, again, it depends on what's available on site and what the costs are. Now, the other option for a closed earth loop is a vertical loop. This is where typically space doesn't allow us to do horizontal earth loops. So we're going to do boreholes in the ground, and we're going to insert tubing that has a U-bend on its end down into these boreholes. And these boreholes can be as deep as perhaps 500 feet. Again, sizing calculations can help you determine how deep do they have to be, how many. Typically, they're about at least 20 feet separation between them. But this is a common configuration in areas where you have limited land space around the building, and we need to get that pipe in the ground. It does tend to be more expensive from what my experience has been than a horizontal earth loop, but it may be the only option if you have space limitations. It's not uncommon to see these under parking lots in commercial structures. When they're properly constructed, right materials, once they are done, you literally cover it up and pave over it, and you hopefully will never be touching that again. Now, a lot of people ask, how much pipe do I need in the ground? And here's just a rough ballpark. And I did it for a slinky, a 4-pipe square that we talked about, and a single vertical U-tube. And you see these numbers over here. These are feet of trench or feet of borehole per ton of heat pump capacity. Remember that a ton is 12,000 BTUs per hour. Typical residential systems would run between about, well, maybe a low end of 2 tons and a high end of perhaps maybe 7 or 8 tons, depending on the size and the insulation. So this can give you some idea of the amount of pipe. There's a reference here that I'd highly recommend. This is a relatively new publication from the International Ground Source Heat Pump Association. It's got some good design tables in it, so you can pin down these tubing requirements better. Over on the left, what are things that improve or decrease the amount of pipe? Well, higher average soil temperatures. If you're heating a building in Oklahoma versus one in New Hampshire, you're going to have higher soil temperatures. That's going to reduce the earth loop length. Wet soils are good. High-density soils are good as well. The deeper the tubing is placed in the earth, the warmer that average temperature is going to be. Larger tubing does have some effect on it, although not a huge effect, not a proportional to diameter effect. And basically, you take the opposite of things that decrease the required earth loop size, things like light soils, dry soils, close tube spacing, shallow earth loops. The calculations are going to show you that it's going to increase the amount of tubing that you need. My recommendation, get a hold of that manual and or some software. Many of the manufacturers offer software to help you quickly pin down what these earth loop requirements are. Let's talk briefly about putting some pipe together. One of the most common piping materials today for earth loops is high-density polyethylene. This is not cross-linked tubing. This is not PEX. Although PEX can be used, the tubing we're going to talk about now is not cross-linked. And what that means is that you can join it together by this process called fusion. And that's essentially heating the plastic to its melting point and then pushing pieces together and letting them re-solidify. With the proper equipment and procedure, that's an extremely reliable, extremely strong joint. It's the same joining procedure that utilities use for gas service. Now, socket fusion is a type of fusion. Essentially, it involves fittings and pipe, much like PVC. The difference is, instead of any type of adhesive, you're using heat. Essentially, you put the end of the tube into a special fixture that you can see over here on the right. This is a heating tool. It heats the outside diameter of the tubing, and it simultaneously heats the inside diameter of the fitting. You pull them apart, you push them straight together, you don't twist it, and those materials, once that polyethylene re-solidifies, you've got essentially one piece of plastic. Extremely strong. So socket fusion. Now, let's switch over a little bit. Caleffi recently introduced geothermal manifolds. See a lot of products like this in the European market. These are newer in the North American market, but those of you that are familiar with radiant heating will certainly see what's going on here. This is essentially a high flow capacity manifold that's assembled in segments, and it's designed using materials that are suitable for earth loop applications. This doesn't have to operate at 180 degrees Fahrenheit, so it can use a polymer material rather than brass material. But the manifolds can be configured for different numbers of circuits. They can be configured with isolation valves, flow meters. So many of the features that that some of you are used to on radiant manifolds. These features are available with geothermal manifolds. Now, again, here's a fairly long list. These are some of the advantages of manifold-based earth loops. One of the things that's nice about a manifold-based earth loop is that you could literally put the earth loop in without any fusion equipment. High-density polyethylene pipe, you can buy that in 1,000-foot lengths. You could design, for example, a 4-pipe square so that there is no seams, no joints outside the building. Bring all those circuits in, and we'll look at some of those details in a minute, and join them up to this manifold. So we call that a fusionless earth loop. And if you're doing an occasional earth loop, you may not have access to those tools. And those tools are they're expensive. Fusion tools can run at least $3,500 for a good setup to do, I'll say, residential-sized earth loops. It has other advantages. It eliminates the need for reverse return piping and changing pipe sizes so that effectively with the traditional North American approach, you're manifolding outside the building, but to keep the flows balanced in the earth loops, you're having to change pipe sizes, keep the pressure dynamics comparable. Now, jumping down here, when the manifold, the geothermal manifold includes isolation valves, you pick up additional advantages. One big advantage is how you fill and flush the system. We've done some calculations on this, and filling and flushing a valveless system requires a substantial pump, about a 1.5 to maybe 2 horsepower swimming pool pump, just to get the flow in the head to simultaneously push fluid through all these parallel earth loops and displace the air. With the manifold approach with a valve, you can do this by isolating all but one circuit and flush that one circuit out just like you would with a radiant floor. So that allows you to use a much smaller purging pump. It also would allow you to isolate a manifold if you ever had a problem. It's unlikely that you will, but if somebody did an excavation, ruptured an earth loop, that could be isolated from the others. Potentially, you could even extend the manifold. So many of the advantages that come from manifold hydronic distribution systems on the heating side are applicable with these geothermal manifolds as well. Here's some details of how you might penetrate a foundation wall. Assuming you're, let's say, doing a horizontal earth loop. We're assuming here a concrete foundation wall. You would do a borehole for each tube coming through. And then a question often comes up, how do I seal that pipe so I don't have water from outside the foundation leaking into the basement? The answer is not a tube full of silicone caulk. The answer is to use one of these link seal type products. This is a compression fitting. There's several on the market now, but you'll see the basic idea here is that you slide this link seal product around the pipe. It goes between the pipe and hole, and as you tighten these bolts, it compresses a flexible rubber seal that goes out against the concrete and the pipe. And these are rated for about 20 psi. So these are definitely strong enough to keep groundwater out, and it provides a professional way to bring that pipe through. And then you'll see some elbows down here at the bottom. Caleffi has some fittings available, and these are, again, elbows that can be attached without any fusion equipment, essentially a compression fitting. That gives you a nice tight 90-degree turn, and from there you can mount your manifold on the wall. Now, there's also the possibility to mount the manifolds outside. They can be done in what we call a vault. It could be a lot of different things depending on what's available. This one shows a cylindrical concrete vault that you might use, for example, for a dry well. And you see the manifold is inside there. The tubing comes up underneath. It's an open bottom vault. And then I'm showing a PVC drain pipe in the bottom. We don't want water accumulating, even though in theory it wouldn't do more than just kind of muddy up the manifolds and the piping. Putting a drain in there and draining any potential groundwater accumulation out is going to keep that dry. Here's another possibility over here. This one is using a sealed vault, so there's no, there shouldn't be any groundwater in there, and you'll see all the piping penetrations are using that link seal type product. And then it has a sealed cover that finishes flush with the finished grade. Just to show you that there are products coming on the market now. These actually were shown at the ISH show in Germany. These are two German manufactured earth loop vaults, and they're all polyethylene. You see the tube stubs coming out the side. These are designed to have socket fusion of earth loop circuits, and they have a nice gasketed lid that goes on them. I'm not aware of any product yet in the U.S. market, although I suspect we will see products like this that, again, gives you a pre-engineered, pre-manufactured way to build a exterior manifold vault. I just want to show you this to show you this concept of manifolded earth loops is not just for residential or small systems. These are products that are made in the U.S. These are for large commercial geothermal systems. You see over here on the right, there's basically a supply and a return header. Every one of those circuits has a valve. Down here, you'll see the tube stubs coming out through. And this whole assembly gets lowered into a hole, and it's actually put on top of a ballast to make sure that it's not going to come up. And some of these have ladders and lights and manhole hatches and so forth. It's like your own personal geothermal submarine. Yeah, this is an interesting slide. Over on the left, here's a traditional North American earth loop setup where we've got that circulation module with the purging valves. We have a non-valved earth loop with parallel circuits, and then we have the heat pump up at the top. Over on the right is the approach using a geothermal manifold. And you'll see several differences besides the use of the manifold. One is you see an expansion tank. I'm a firm believer that earth loops should have expansion tanks. That fluid does heat and cool. It does expand and contract, and so does the piping. And without an expansion tank, you can have some fairly wide pressure fluctuations in that loop. Where the problem tends to come up is in the cooling mode, where the pipe actually expands faster than the fluid. The pressure in the system can drop, and I have seen it drop to the point where it will actually cause a cavitation in the pump. By having an expansion tank in there, you can stabilize that pressure. Dirt separation is another nice detail. Obviously, you're putting a lot of pipe together. If you're putting it together in the field, in the trench, you could get some dirt in there. There may be dirt in it when you buy it. So a dirt separator is going to clean that out. And, of course, this is a continuous recirculation closed-loop system, so that dirt separator it's a very high-efficiency product. Eventually, it'll get very, very small particles out of that fluid stream. So basically comparing these two, you see the difference between a manifolded and what I'll call a fully trimmed system, which is quite honestly very characteristic of systems you'll see in the European market versus the kind of the traditional North American approach over on the right. I don't want to knock either one. I simply want to say the one on the right does bring some advantages in terms of hydronics. Now, just another slide I threw in, just so you know, there are gas-fired heat pumps available in the U.S. market. Rover is one manufacturer, and then Fulton Boiler actually works with an OEM product. And these are operated by either propane or natural gas. They don't involve compressors. They do basically an ammonia water absorption cycle. They have some impressive performance characteristics, and they can be tied in with earth loops using essentially the same type of technology we've talked about. These are actually capable of some pretty high temperatures, 140 degrees Fahrenheit, and they can operate with earth loops down to 23 degrees Fahrenheit. So they actually have a slightly wider range than the vapor compression heat pumps. Now we're coming down the home stretch here. I just want to very quickly give you some heat emitter options. The key with successful hydronic heat pump applications is keeping that water temperature in that distribution system down. Okay? We've got to have low water temperatures. So how do you do that? Well, radiant panels, radiant floors with low resistance covering, radiant walls, radiant ceilings, these can all operate. My suggestion is to keep your design water temperature that's supplied to the distribution system at no higher than 120 degrees Fahrenheit. Okay? Residential baseboard traditionally is pretty much out. especially in a retrofit, oftentimes people will say, can I just disconnect my boiler, connect the water-to-water heat pump, and operate on my baseboard? And typically you can't, because that baseboard has been sized for a much higher temperature. You can size it for lower water temperatures, but you need a lot more baseboard, and typically you don't have the wall space to do it. Later on, if you get the PDF file, there's a graph here you can go back and actually see how much baseboard would I need, for example, if I want to limit my water to 120 degrees. Here's a relatively new product in North America. I put it in just to show you that times are changing and products are evolving. This is a very large thin area, thin tube baseboard. It's actually made in the UK, but it's available in the US, Smith Environmental Products. To take a look at some of those output ratings, these are roughly about 3 times the output of standard residential thin tube at the same water temperature. So if you want the combination of baseboard along with a heat pump, this is a product that you could take a look at. This is something you should never do, heat pump or not. Plateless stapler is, well, it's something I have only seen in North America, perhaps up in Canada. You just don't see this being done in other parts of the world. This is going to require very high water temperatures, well beyond what a heat pump's going to do. So you see the big red X's, stay away. Radiant floor heating with low resistance finished flooring or no finished flooring, like a slab on grade. It's a good option. Again, there's a performance table that you can take a look at later on based on the finished floor resistance and the tube spacing. Essentially, low resistance flooring and close tube spacing is going to give you the lowest water temperature and allow you to get the best COP out of that heat pump. Thin slabs, many of you are familiar with these. This happens to show one made with concrete, 1.5 inches of concrete. This one shows it made with a poured gypsum underlayment. Take a look at that tube spacing there. You'll see the tubes are close together, about 6 inches on center. The closer the tube spacing, the lower the water temperature. And that's going to enhance that heat pump. And it's important to realize that the tubing is a relatively small part of the cost of the overall system, and the performance savings are there for the life of the system. So when it comes to tube spacing, be generous. Radiant walls, some of you have probably seen this in some other writings that I've done. A good performer, very adequate at 110, 120 degree water temperature. It uses tube and plates. Just some examples of it here. This is actually a radiant wall built into a staircase. Here's an infrared image showing how it performs. Those heat dispersion plates do a good job. Same construction up on a ceiling. I'm very convinced that radiant ceilings are going to be a up-and-coming sector of the market, even more so in the future because of the ability to do cooling as well as heating and have a nice, simple, unobstructed, low-mass surface. Panel radiators are a possibility, but make sure you derate them for the lower water temperatures. Most manufacturers give you ratings at higher water temperatures. That's what this table shows, along with some kind of a correction factor for those lower temperatures. Again, like with thin tube baseboard, plan on about 3 times the surface area on a panel radiator if you're operating it at 120 degree water versus 180. Yaga North America has products out, these low H2O panel rads with the micro fans. They have excellent heat output characteristics at low water temperatures. These products are really designed for heat pumps in the European market, and they're now becoming available in the North American market. And as we wrap up here, I just want to point out that Caleffi will very shortly be releasing Hydronics number 9, which is on GEO-hydronic systems. Some of the graphics that I showed you today are in there. There's a lot of schematics in there, a lot of other information. It's the largest issue to date. I would certainly recommend you get a copy of that. It can be downloaded from the Caleffi website as a PDF file, or if you register, you can also have that mailed to you. And again, our reference that we talked about earlier, the Residential Design and Installation Guide from International Ground Source Heat Pump Association. And just a reminder, before we go to questions, this is part 1 of a 3-part seminar. Bob Rohr will be doing parts 2 and 3 on those dates, and we're going to kind of pick up from where we left off here today, getting into some specifics on the construction of the earth loop, as well as many different schematics for how to do geohydronic systems, single heat pumps, multiple heat pumps, how to tie it in with solar, how to tie it in with storage systems. Tremendous versatility once you bring hydronics into the mix. So with that, I see we're pretty close to 1 hour. I'm going to turn it back over to Bob and questions.
Well, great. That's exactly what we needed. I think that was a perfect introduction. I think everybody that's watching can see how this can tie in so nicely with solar. When we start talking these low temperature emitters that work with the ground source systems also work well with solar. So that's what we'll be going into in the next 2 sessions, is how to integrate those systems, because they work so well together. So I think you answered some of these questions, but let me run by quickly here. There's only a handful. I think most of them you got to as you're going along. And one was, let's see if I can read these off. What about cool, cold water radiant, which I think you just touched on, instead of using the air for the distribution, which I think you touched on that, but certainly the dew point becomes an issue with that, if you want to talk about that.
Sure.
A little bit.
Yeah, radiant cooling is, again, a sector of the market that is growing. Initially in the larger building sector, but there's a lot of interest in radiant cooling now in residential. It certainly is a good tie-in with a water-to-water heat pump as the source of the chilled water, but as Bob points out, it's critically important that you avoid the dew point temperature on any radiant surface. And there are controls on the market, and more coming, that can measure humidity and temperature and calculate the temperature that the surface would need to reach to form condensation. And then it's simply a matter of keep that surface 2 or 3 degrees above the dew point to prevent condensation. And the moisture removal has got to be done through a separate air handler or some other device where condensation can form and be collected without damaging the surface. But I definitely see radiant cooling and geothermal water-to-water heat pumps as a growing market.
Great. Another one, I think you probably covered this a bit. So if you want to keep as much heat in the ground, wouldn't it be better to send the heat to the ground instead of putting it in the domestic water in the cooling mode?
The problem there is how much of that heat do you retain? It would be nice to think that all summer long you could dump heat into the earth loop and simply store it in the ground and then pull it back in the fall from the winter. There are some projects that have done that. In fact, I was just reading something a couple days ago, and the estimate was that about 30% of that energy that goes back into the ground is lost. And I'm sure that goes up if there happens to be a high water table that would tend to purge that heat away. So it's an interesting theoretical concept, but it's very subject to the local geology. And I don't see anybody yet that has got a packaged approach out there. Okay. Any other questions coming in, Bob?
Yeah, let me do 2 more. I know a little over time here, but it looks like people are staying on the line, so we might as well get them so everybody can take advantage of these. Somebody asked about the dirt separator, a combination dirt-air separator. Certainly that would be an excellent idea. And they questioned about the plastic tubing shavings floating instead of sinking like sand and dirt. But if you look at the type of separator that most of them out there, and ours is also, it captures it in there and causes it to fall in the chamber. So I think I'm going to show a clear demo of that in an upcoming webinar, that we actually put some plastic shavings in. We built a clear plastic tubing separator with a bunch of tubing. I threw copper shavings in there and dirt and all kinds of things to see how that works. And I think you'll see that it does, in fact, collect those shavings and force them to the bottom. So we'll get to that in another webinar that we're going to do.
Yeah, another quick point on that, too, Bob, is that probably most of those shavings are going to be blown out during the initial fill and purge.
Yeah.
And Hydronics 9 goes through the whole procedure of how to set up a purge pump and set up hoses to essentially flush the air out and get the fluid in. Most of that plastic will probably come out at that point, too.
Yeah, that's a good point. I mean, that's the same with the hydronic system or snowmud or anything. You want to do most of the big heavy lifting on the dirt removal with your initial purge, but certainly anything that's left in there, you want your separator to be able to handle properly. Jointless vertical ground loops would still require a fused U-bend. Now, I know one of the installers in my town actually buys his U-bends right from the factory with that already fused on it, so he doesn't need the machine to do that. He just tells them the length and the size he wants, and it comes with that. It comes coiled up in a nice bundle with that joint already on it. I guess that would be one if you don't have the equipment.
Yeah, I mean, it's a good point. Yes, the U-bend does have to be fused, whether it's done on site or whether, certainly if the goal is to try to stay away from any fusion on site, to avail yourself of products like those pre-built U-tubes.
Yeah. Should we be designing systems with a larger delta T when we're using the water-to-water GEO unit?
Typically, no. When you go to larger delta T's on the condenser, your performance is actually going to drop because the way you're going to get that larger delta T is with lower flow rates. Again, I would suggest nothing lower than about 2 GPM per ton on the evaporator side or the condenser side. Again, below that, you're going to start to lose convection, and you can actually go to manufacturers' rating tables or graphs, and you can see that as you lower the flow rate on either the evaporator or, in this case, the condenser, there is some incremental drop in performance. Now, it's not big. You have to kind of weigh that against the trade-off there. Perhaps you might go to a smaller pump and a slightly wider delta T and be willing to accept a slightly 1 or 2% drop in performance. But in general, there's no inherent advantage of going to a wide delta T on the load side of the heat pump.
Okay, good. Let's do 2 more here, and then we'll wrap it up. Somebody just a comment. Somebody mentioned there's a solar dehumidifier available on the market now. That might be worth looking in Noble Air, N-O-V-E-L-A-I-R-E is the name you mentioned. Yes, the PDFs for everybody will be available. All the questions that you're sending in also come to me in an email form. We get this little spreadsheet at the end of the webinar, so I'll be able to send anybody that's asked for that. I'll have your email at the end here, and I'll get those to you as soon as I can. Emails, yeah. Okay, will you discuss more efficient pumping, lower wattage in the upcoming? Yeah, we're going to touch on that some more about. I think he's talking about using ECM pumps.
Yeah. Yeah, a lot of the schematics in Hydronics 9 do have ECM-based pumps and essentially leveraging this concept of valve-based flow control in combination with a variable speed pump, both on the earth loop side and on the load side.
Yeah. I don't know basically what the answer with this. What about DXGEO? I think he's talking about direct exchange where the copper tube with the refrigerant goes right into the ground instead of going through the heat exchange.
I'm going to admit I don't know a lot about it other than it's out there. I think there's at least a couple manufacturers that are doing it. It involves quite a few different processes, specifically brazing up quite a bit of copper in the trenches. In theory, it has a performance advantage because you're eliminating the water between the soil temperature and ultimately the refrigerant. But it's really a whole different set of tools and techniques compared to what we're talking about here.
Best to go to the manufacturer for that information, I would say.
Mm-hmm.
One more, let's do. What's typical for a typical 4-ton GEO unit using an open loop connected to the closed loop? Sizing the heat exchanger. I think that would be something for probably the heat exchanger manufacturer would want to know flow rates and temperatures on that. And I know there's some online calculators available for that.
Oh, yeah. That's, I think, referring back to that pond system that I showed.
Right.
Again, you want to be generous in sizing that heat exchanger. I would say probably the approach temperature difference no higher than maybe 5 degrees Fahrenheit. We don't want to impose much of a thermal penalty between the water temperature that the heat pumps are seeing and the water temperature from the source. Because, again, it just shifts us to that lower COP and lower capacity. So it's a trade-off between the cost of a larger heat exchanger versus the performance degradation due to the fact that there is a heat exchanger in there. But I'd suggest a starting point of no more than 5 degree Fahrenheit approach temperature difference on that heat exchanger.
All right. Well, a question on when Hydronics 9 is going to be available. I don't know if Woody and Rex are still on the line. I think are we at the printer with that right now? I know we're really close. We aren't. We had to change a couple graphics and things, but that should be coming out within the next few weeks to month, I would say. I think it's at the printer. So do you know?